Hi folks, we're going to talk about simple harmonic oscillators, specifically a mass on a spring. All right, you might be able to imagine the following. Imagine we took this system, this mass on a spring. All right, here's a spring that attaches this mass to the wall, let's say. And let's say we took this whole darn system and let's see, we do this and we sort of turned it like this, or you know, that's still the floor. And then we take this piece of, like, we take this thing, oh boy, we take this, and this is, imagine like a piece of paper, right? And we take the mass and we displace it, right? We take this mass and we move it, you know, displace from equilibrium, and we paint the mass, right? The bottom of the, or the mass is a block of chalk. Yeah, but frictionless. But how to draw? You get me. And so what we do is we take this paper and we attach it to something that feeds the paper like this at a constant speed, and the mass is oscillating back and forth, right? It's doing this, oscillating back and forth, and as it does that, what it would do is make a pattern of that oscillating back and forth as this paper moves, you know, underneath it, let's say. And what you get is a pattern that looks like that. All right, now it looks like that, but let's talk about the specifics of that form, of that pattern. Now, the way that we'll do that is we're going to do a dynamics, or a investigation of forces that are acting on this object, specifically when it is displaced. All right, so let's say because look, this says in the beginning, at time 0, this thing is displaced by a meter. So let's call this equilibrium position, and let's put the object over here, 1 meter away from equilibrium position. And I'm not going to draw the spring, but I'm going to draw what the spring does. And the spring does this. It applies a force by the spring. So if we say net F, right, well, that is F spring equals MA. Okay, now how hard does this spring pull? Well, that depends, right? Hooke's law says that spring force equals Kx, is proportional to displacement, and the constant proportionality is this thing called the spring constant, depends on how, quote, stiff the spring is, right? So this says Kx equals MA. Now, a couple of specifics we can add to this. We can say, I'm going to do this, Kx. Well, the position isn't going to be a position. The position of this object is going to vary as a function of time. And that means that the force is going to vary as a function of time. And that means that the acceleration is going to vary as a function of time. So I can do that and say those position and accelerations, yeah, those are both functions of time, sure. And the other thing we can say is, note, this thing was displaced this way. Here is a delta x, or an x, same thing. All right. And so you'll note that when this thing is displaced to the right, the force and acceleration is to the left. The acceleration and the position or displacement are in opposite directions. And furthermore, look at this. This really says that A, as a function of t, is, well, how about this? Negative k over m times x as a function of t. And these are vectors, and that's why this negative is in there. So this is a really important result. And it's important because of how acceleration and position are related. Well, acceleration is the time derivative of velocity, and velocity is the time derivative of position. So that means that acceleration is the second derivative of the position function with respect to time. And so what this really says is, well, the second derivative of this position function is proportional to the function itself. I'm letting that soak in. The second derivative of a function is proportional to but you know, has this negative in front of the function itself. Well, guess what? There is only one function in the universe for which that is true. There is only one function for which the second derivative is proportional to the function itself. All right, I'm going to step through a couple of slides and say, well, let's look at this second. Let's look at the first derivative of this thing, right? Here's position, here's velocity. Remember, velocity is the dx dt. So really, this is the instantaneous slope of the position function. All right, so our velocity function says, okay, what's the slope of this thing now? Well, it's 0. All right, well, what's the slope of this position function now? Well, it's, quote, big and negative. Well, what's the slope now? Well, it's 0 again. What's the slope now? Well, it's big and positive. What's the slope now? It's 0. What's the slope now? It's big and negative. What's the slope now? It's 0. What's the slope now? It's, whoops, now it's big and positive. So watch what we get. We get this. Oh, that's pretty nice. It was all right, okay. All right, so we get that function. And then, well, let's see. If I take this function for velocity, and we say, okay, here's acceleration, and acceleration is the time derivative of the velocity function. Acceleration is dv dt. That says that acceleration is the instantaneous slope of the velocity function. So the instantaneous slope of this velocity function, well, right now is big and negative, and right now is 0, and right now is big and positive, and right now is, oops, 0, and right now is big and negative, right now is 0, right now is big and positive, right now is 0, and so we get this function. So if you go back to the first function, the position function, look, the position function was big and positive 0, big and negative 0, big and positive 0, big and negative 0, big, and the acceleration function is big and negative and then 0. So the acceleration function looks like the position function, but in the opposite direction, right? I'm going to sketch on here our acceleration function looked like this. Now, we can't really draw them on the same axes because they're not measurements of the same thing. Oh gosh, that's terrible. But qualitatively, I'm trying to, on purpose, sort of draw them at different scale. Oh god, at different scales because they can't have the same scale. So I'm just trying to show it like there's no rule about their amplitudes being the same. But the acceleration function looks something like that, which says exactly what this says. It says the acceleration function is just like the position function, but with a negative constant multiplied by it. Okay, and there is only one function in the world for which this happens, and that function is a sine/cosine function. A sine and cosine function are the same function, just shifted relative to each other. So it's okay to say sine or cosine. So what this says is when you get to a situation, a phenomena, a system for which that statement is true, which says that the second derivative of the function has to be proportional but negative to the function itself, there is only one function that can meet that criteria, and that says that this position has to be, quote, sinusoidal. All right, now this one happens to start at a max, so this is actually a cosine function. That's okay. So this is a cosine. Well, and the amplitude of this function is what I'll call x max. And this function has some, well, depends on time, and there is some rate at which the function repeats itself. Okay, this omega is called angular frequency. And that has to do with how often the function repeats itself. Specifically, that omega is 2 pi over t. 2 pi being an entire oscillation and t being the amount of time for one entire oscillation. So 2 pi being the number of radians in this full cosine function, and t being the period, the time it takes for an entire oscillation. So this has to be the case. X has to be that kind of function. Because again, there's only one function in the universe for which the second derivative of the function is the function itself with a negative constant in front, and I'll show you. Because, well, if this, our position function again is x as a function of t is x max cosine omega t, well, this velocity function, a couple of things. One, by definition, v, like we said, is dx dt. So if we take the time derivative of this position function, we get, well, all right, so first of all, we can actually take it right from what we've drawn here. You know what this function is? That's a starts at 0 but goes negative. That's a negative sine function. And guess what? It has the same rate at which the function repeats itself. Well, it has to. We have to keep this part because of sort of by definition. Well, I'll get there. Watch. What's this number? What's this amplitude? Well, it's not an x max. It's a v max. So how do we justify this? The time derivative of this function really is, so dx dt is, well, first let's do the derivative of the cosine part. We got to keep this, that's a constant, so that's x max. Now the derivative of cosine by definition is negative sine. And then maybe it's called the chain rule, I think, says we have to also take the derivative of this part with respect to time, and that's omega. And what's x times omega? Well, it's meters and radians per second. Yeah, that's a meters per second thing. So the rules of calculus say that this is the derivative of the position function, but we can also see just saying, well, rate of change means okay, and okay, and okay, and so we can, it just draws itself correctly. All right, now look at this. If here is v as a function of t is, I'll write it like this, omega x max negative with a sine and an omega t. Well, acceleration function, one thing is we can look at this function that we've drawn here and say, well, that starts at -1. That's a negative cosine. So a as a function of t looks like, well, it's got to be an a max for the amplitude. It's a negative cosine, and it repeats itself at the same rate that the other two functions do. Well, the rules of calculus say that a is dv dt. So when we differentiate this function with respect to t, well, we got to keep what we had, the negative omega x max, negative omega x max. The derivative of the sine function is a cosine function. Then we have to differentiate the omega t with respect to t. That gives us another omega. So look, this turns into omega squared. And yeah, omega squared x is a max, because x is measured in meters and omega in radians per second. So omega squared in radians squared per second squared, but radians aren't a unit, right? So those units check out. That's definitionally true, right? So look what we get. I'm going to take this and bring it back here. We get that a as a function of t was negative omega squared x max cos omega t. Right? We just said that right here. Negative x max cos omega t. So look at this. We have the position function is this. it's there. And so the acceleration function is a negative constant times the position function. That's what we said here. The acceleration function is a negative constant times the position function. So we have proven that the function that describes this thing's position, this oscillator's position as a function of time, is a cosine slash sine function. In this case, a cosine because we said it started at a big positive. And furthermore, what we can say is, well, if these two expressions are analogous, then this and this are the same thing. So that says for a mass spring oscillator, it says that omega squared is k over m. Not omega squared. Well, omega squared is k over m. So omega is the square root of k over m. And remember, omega is 2 pi over t. All right? So this is 2 pi over t is radical k over m. So we can talk about the period of a mass spring oscillator, and that is 2 pi m over k. I'm still here. Are you still here? So that means, well, it means a lot of things, right? Remember, I'm going to sort of walk us through this process. We did a net F to get to a place where we said, hey, the position, well, and the acceleration are related, and furthermore, they're proportional to each other. And here is a constant of proportionality. And there's a negative in there. And there's only one function for whom acceleration, being the second derivative of a function, is proportional to the function itself, and it's a cosine or sine function. And then we derived what the velocity and therefore acceleration of this system is, and showed specifically that, yeah, look, these two things, so many arrows, these two things do relate. And when I say these two things, I mean this statement here, right, that a net F analysis says that, well, position and acceleration are directly related, and these two that says position and acceleration are directly related, right? This says position and acceleration are directly related, and there's our constant of proportionality, right? And we said here's our constant of proportionality, and thus we can set those two things equal. Omega squared is k over m, or omega is the square root of k over m. And again, this omega is the rate at which this function repeats itself, which can be related to how long it takes the function to repeat itself. And this says, well, the more massive mass is on the end of a spring, the longer this thing takes to repeat itself. But the stiffer the spring is, the less time it takes to repeat itself. That, you know, logically checks out. Okay? Whew, kind of a lot there. Now, let's talk about it a little more. Let's talk about energies associated with this oscillator. Well, we know that energy stored in a spring is 1/2 kx squared. So this energy must vary as a function of time. K, well, with x of t quantity squared. So that means that u spring as a function of time is 1/2 k, let's see, x max squared cosine squared omega t. And look, what's this? What's 1/2 k x max squared? That's u max. So there's some u max that's biggest when this is biggest, when position is biggest. Guess what? U is also biggest when this is biggest. That's a big displacement. All right, and so what we're kind of doing is squaring all these values, but the amplitude is different because the amplitude is not a position. The amplitude is a energy. So this says big, 0 energy, big energy, 0 energy. Yep, big energy, 0 energy, big energy, 0 energy, and we get this. So this has a different frequency because of that squared in there. If we look at kinetic energy as a function of time, okay, K is 1/2 mv squared. Well, velocity varies as a function of time, and thus so does kinetic energy, V as a function of time, quantity squared. So let's see. What I need to have, so let's see, K as a function of time is 1/2 m. Remember, our velocity function, I'm going to just write that down here, from a couple slides ago. Here's our velocity function. Negative Vmax sine omega t. So this is going to be, well, but if we square that, we're going to get Vmax squared sine squared omega t. Okay, and look, right, here is Kmax. And right, it's a squared sine function because, right, what's velocity now? Velocity is 0. When this thing instantaneously comes to a stop and comes back through a stops and goes back through stops and comes back through and stops. So K is 0, velocity 0, slope is 0. So K is 0. K is big, end of story. It's not big and negative. That's fast. Fast velocity, big K. No velocity, no K. Big velocity, big K. No velocity, no K. And so on, and so on, and so on. And so this thing looks like yay. And check this out. If I were, it's kind of a pain in the, so this U starts big, gets small. K starts small, gets big. Let's put them both here. Here's U as a function of time. Here's K as a function of time. What happened? U started big, got small. U does this. What did K do? K started at nothing, got big. And guess what happens when you add those up? I mean, we could probably really actually do it, right? We get let's call it, we get let's see, U as a function of t plus K as a function of t. This was 1/2 K x max squared cos squared omega t plus 1/2 m v max squared sine squared omega t. Okay, I switched gears, folks. I had to spreadsheet this stuff for myself just because I didn't really know how to make the justification for you. But look, I plotted, here are a bunch of times that I chose at hundredths of seconds intervals. Look, I chose an X max for a mass spring oscillator and a K and an M, and thus, this is actually, watch this, equals K over M raised to the 1/2. Yeah, good. See? I used a naming thing here in my formulas, the naming manager, to name things, K and M and omega and X max. These things are named. And that helps when I say, like, for example, look, here's U spring. U spring is 1/2 K X max squared cosine omega t squared. The B7 is the time, right? So this one, like, uses that time, and this, oh boy, hang on. And this one uses that time, but they all use omega and X max and K. That's a nice thing about that naming, that name manager. So look, I've got these and here's K, right? 1/2 m. Well, this is Vmax. Omega x max is Vmax. Okay, here's Vmax squared. I know this is very small and hard to see, probably, but oh, here we are. Sine squared omega t. Right now, boy, oh boy, this is a noisy graph. So I'm going to make this a smaller frequency, and I'm going to do that by making this a big mass. Oh yeah, right. The more mass this thing has, the less often the pattern repeats itself. Great. Let's do this. Looks like more often. That's okay. Now watch this. ME total. Guess what that is? That's equal to this. No. No. That's equal. This is equal to this plus this. Watch this. Do them all. Oh, what? Yeah, exactly. This shows us that mechanical energy. Oh, what's up? For hundreds and thousands of data points. Yeah, these mechanical energies are all the same. Can I do this? What if I were to do this? What if I were to include, oh, what's up now? Oh, boom! This is a plot of mechanical energy as a function of time. It's constant. Oh my gracious, that's wonderful. I mean, have you ever seen, why is K 4.27? Let's make it something like 4. Yeah, sure. Now watch. What if I were to increase this initial maximum position by a factor of 2 to turn it to 2? Guess what happens to energy? It goes up by a factor of 4. Oh yeah, because U spring is 1/2 kx squared. So if I double the elongation or the displacement, I quadruple the energy. This gives us a great justification for why this is a constant. I faltered with the trig identity stuff. It's in there somewhere. But the bottom line is we can plot both of these, both that we can add, quite literally add these functions, add that U and K function, and what you get is the fact that this system has a constant mechanical energy. Because spring forces are conservative for reasons about path independence of a work done and network around a closed path being 0. That's conservative force talk. But this gives us a real quantitative justification that mechanical energy for a mass spring oscillator is constant or conserved. All right, and those are all justified by the fact that, well, Newton's second yields a very special result when we analyze this system. And that leads us to a very special relationship for whom there is only one answer to this equation. And that answer is, or solution to this equation, that here's the solution. This is the rule, what x must be as a function of time. In this case, x, right? For quite literally a linear position of an object. The same thing will hold generically true for the angular position of a pendulum. Because a pendulum is a simple harmonic oscillator, provided that it undergoes only, quote, small amplitude oscillations. All right, so we get an analogous set of solutions for position and acceleration and quite literally velocity also. An analogous set of solutions for a pendulum's equations of motion that lead to, well, that will lead to this really the same thing, not U spring in K for a pendulum, but UG in K for a pendulum. I think that would be a little bit harder to prove. UG is with height, and height for a pendulum and angle are kind of a pain to relate, but we can do it. So the short story here is that a mass spring oscillator is an example of a simple harmonic oscillator, and that definition, simple harmonic oscillator / motion, is that second derivative of function and function are proportional, but there's a negative in there. When you see that as the generic solution to a situation, you have to, as a physics C student or an advanced physics student of some nature, I guess, say, ooh, that means simple harmonic oscillator. That means this has to, this function, whatever this function is, has to be satisfied by either a sine or a cosine. It's okay to start this with a sine, because then your derivative for velocity will give you cosine, and then derivative of that will give you negative sine. And right, we started with sine, we get to negative sine, so that's okay too. That would still satisfy this generic requirement. Okay, so there's the real full justification for a couple of things. One, mass spring oscillator being a simple harmonic oscillator. And two, that mass spring energy is constant. And that was made hopefully pretty darn clear by this beautiful set of data we generated with Excel. All right, watch this. What if I make a, let's see. It's not a very stiff spring. Oh yeah, right. It doesn't oscillate very often because the spring is a little weak spring that can hardly apply much force per unit displacement. Great. And what if we were to make this thing like, oh boy, just a, what if it's a huge, oh, you know what never mind. You notice what's not in here? What's not in here at all? G. This has nothing to do with where in the universe you are. No matter where you take this system, it still behaves exactly the same way. All right, no matter where in the universe this thing goes, it's all these things are constant. All right, well, that's enough. It's enough, certainly, if not too much. Thanks, folks. Bye.